Okay, then let's get started. What do we have today? Last week we talked about smoothing, and I showed you how to smooth by linear regression. And the next thing I want to show you now is another smoothing technique, namely smoothing by spline regression. And we'll need both afterwards when we go back to our biological application. So we go through this a bit. For those who haven't been here last time, and also for us to get back on track on where we started, where we stopped last time, let's have a quick look what the whole thing was about. So you remember the problem setting was we have a curve like this, or we have data points like this. This is we will typically imagine that this is measured data. X is some independent variable which you set in your experiment, and Y is the response that you measure. And you see sometimes for the same X you can get rather different Y values because there's an inherent noise in the experiment which doesn't allow us to always get the same value. And our aim is to get the underlying curve, like to remove this noise in the way how we do. And in order to simulate this case, I have made here a true curve. So I imagine this is the true response onto which I add noise, and that's how I got this value. And then I showed you last time several ways how to get back to this smooth curve. And the easiest is, of course, simply to put this into bins of X values and take the average over them. But then we don't really get a smooth curve, but rather a staircase curve. So what we then did was with kernel smoothing, where we said we make our smooth curve by finding the Y value of a smooth curve for a given X value X naught as follows. We sit on this X naught, and then we take the average over the Y values of a neighboring point, and we make this a weighted average where each neighboring point is weighted according to the distance. And we had this kernel, which was a smooth curve with support from -1 to +1. So outside -1 to +1, it was 0. And within this area, it smoothly ramped up from 0 to some maximum value in the middle and then back down again. And in that manner, we could smooth that. And here I made this nice picture where we can see this. Imagine we want to get the X naught, the Y value for the X naught value corresponding to this one here. When we put this kernel over it, and the size of the points now shows you the weight that we give these data points depending on how far they are from the desired data point. And so we make a weighted average over these ones. And then we had improved this in several aspects. First, we said instead of just taking the average, we can also make a linear regression and fit a line into this thing. And when we fit that line, then instead of simply asking where's the weighted average, we ask where does the line go through our query position. And we fit this line with weighted linear regression. And when we add it, of course, instead of fitting a line, we can as well also fit a parabola by making still a least square fit, asking what is the minimum, what is the least square fit for a parabola going through here. Least square in the sense that the vertical distances from the parabola or the line to the data points squared and added up is minimal. And even though we now fit a quadratic function, this is still a linear fit because we pre-calculate for each data point its X value and the square of its X value. And then we just regress on these two so that the regression itself is still linear. And that's what we did here, where we used the linear model function of R and said regress the Y values on the X values and their squares using the weights, and do this for every point along a long grid. And that way we got here this red curve, which is now quite tight and close to a blue value. We talked quickly about adaptive bandwidth, where we said we can change the width of a kernel so that always the same number of data points are under the kernel. And I told you that instead of, I showed you first how to calculate all this using manual R code, so that you really know what's going on, but we can also use the ready-made lowess function in R, which does this fitting. Lowess is local, no, I've forgotten what lowess stands for. Least occurrence of, it's locally weighted scatterplot smoothing. That's what it stands for. Okay. We tried a couple of uncertainty estimation techniques to see how well our fit fits. I want to skip over this now. When we switched over and said, what if the errors are not normally distributed? In my original case, I said, we assume that there's a true response function given by the blue curve, and our measurement process adds Gaussian, so normally distributed noise to it. But what if the noise is not normally distributed, but Poisson distributed? That's what we did down here, where we said, let's again take a response. This time I took the same curve as before, but I squared it. I exponentiated it. And then I used this as input for Poisson variables, and now I get this, these Poisson counts here, which I have already switched for usually K over S by 10 times 10,000 plus 1, so I did our usual log normalization, and now I can plot. I can again do my regression and get a nice fit, and the trick here was that we replaced the linear regression with a GLM regression, with a generalized linear model, which doesn't try to minimize least square, but it tries to maximize the Poisson likelihood. Now that was a crash run, so what we've done last time, because there were a few people there, but I have recorded it, so if you now want to know the details, you can either just read it, or you can watch the recording, which I've uploaded. But the next thing we can now do is I show you a completely different way, an alternative to the local regression. So we are back, let's forget about this last part which we did with the Poisson regression. We are back to the case where we have Gaussian noise, so normally distributed noise. So we are back at this example here, and we want to get this curve back. But this time, instead of doing local regression, we do spline regression, which is, you will see that depending on application, sometimes local regression seems to be the better choice, and sometimes spline regression seems to be the better choice. And in the single cell field, people use both, and so I wanted to show you both. And now, how does spline regression work? Spline regression, did I start with a spline regression? Here. Spline regression works as following. We say we want to reconstruct our curve, so our true curve, as a linear combination of basis functions. And this here is my function basis that I use. You remember my blue curve went from 0 to 1, and I now try to recreate this blue curve here by adding up these basis functions. And you see they are nicely chosen basis function, because if I have a peak on the left, I can take a high weight on the green curve, and if I have a peak on the right, I might put a high curve on that one. So I can construct quite a lot of different curve shapes by adding up this basis. Now, of course, I've only shown you here a picture of the basis. I don't tell you how I've constructed the basis. That comes 2 pages further down. For now, let's just say I have this basis of functions which all have support from 0 to 1, and by making linear combinations of these basis functions, I construct quite a number of different functions, and I try to find the function, the linear combination of this basis, which gets as close as possible at our true function. And this is something which works surprisingly simple. As soon as you have a basis, it again is just a linear regression problem, and that's the beauty of the whole thing. So first, I tell you later how I have constructed these basis functions. Now I first tell you with what properties in mind I have constructed them. Each of these functions here are piecewise cubic functions. So, for example, the light blue function here, this is a cubic polynomial from here to here, then another cubic polynomial from here to here. So from each gray line to the next gray line, it is a cubic polynomial. And And the cubic polynomials are such that when you switch from one to the next by crossing a gray line, we made sure that it's continuous and differentiable, but it will turn out that the second derivative is makes a jump at these places. And so we can use different degrees. These are all third-degree polynomials, and they all partition the unit function, the unit. So if I go to a random x value and add up all the basis function for this value, I get exactly 1. And with this, we can now try to make a regression. And I show you here how this works. Again, let me load this code when I can show you this live. GLMs, this is what we all already did last time. Yeah, this is where we got this time. So, here you see I again make my, no, this is not, still not ein Steuerung. Why is this actually bad, big? Is this too small now, or can you still read it well? Let's make one bigger. Okay. Here I have an outline when I can switch here to spline. Very good. So, okay, this here is my basis splines, and as you can see here, I have this function bs, which comes in the spline package and that constructs this basis. And I also have made here this xg. xg is just a vector of 300 numbers which span the values from 0 to 1. So it means x grid, and I will use this all the time to draw my stuff. So I ask this thing here, produce for each of these grid values, give me the different spline values. So these here are the x values, and this is the y coordinate of the first, second, third, fourth, and so on spline. And as you see, 5, 6, 7 are 0 at the beginning, but then later they come out. And here is, and now let's make again our true function. I calculate random x values and evaluate my function at this y value and add some random noise to it. And then of course now I have again as before x, comma, y here this thing where I want to make my smooth stuff through. And what I now do is I calculate our spline function at the coordinates of the actual data point. So xg is the unit space grid, x is the actual data points. And for each of these data points, how many do I have? 100 data points. I now calculate my spline basis at these things. And then I get ES up to here. And when I have now this function mybs, it takes an x, and if I say mybs 0.3, then this function just calculates each of these three basis functions and gives us the first basis function has 0, the second has 0, the third has this. So these are the values of the 10 basis function at the position 0.3. So these 10 functions. And now I'll tell you later how I construct them, but for now let's just have them, say we have them, so I can calculate the basis function at all the actual x values. And when I get here this thing, for each x value of the data, I get the corresponding y value of the basis functions. And now I can say the y value of the data should be constructed as a linear combination of these values. So it's exactly the same that you do in ordinary linear regression. You're looking for 6 coefficients beta, which you can put in front of these things to produce all these basis functions. And this is why I can just call the linear model fit function and say it, solve this linear model problem where I say these block of x values here multiplied with a vector of coefficients of 6 coefficients should get as close as possible to these y values, as close as possible in the sense of minimizing the square of the differences. And if I do this, I get here these coefficients, and it tells me if I sum up the basis function according to these coefficients, I get this. So let's try this. Here is the Here you see the blue one is the true curve, and the red one is my regression. And the way how I did this red curve is I just take all these, again, this block of values of the individual basis function and multiply with my coefficient to make the linear combination. So that's how I get through this. And now, what I do now next, but if you look at it, we are still a little bit unhappy because it's quite wiggly, the red line. And that is why, because this thing is, of course, happy to take all these little wiggles of the basis function. And now in spline regression, there's the trick that you penalize your regression. You say, I don't want to optimize the least square, but I don't simply minimize the least square, but I want to minimize something like this. Here I've written it properly. So this, so far we have just said we want to make a linear combination of these basis functions such that the distance between the data y values and the fitted y values is minimal if you add up the squares. And now we replace this here. Here we still have a least square criterion, and I add to this something else, namely here the integral over the second derivative of my function. Because the second derivative tells us how wiggly this is, and I square the second derivative so that a very wiggly function will have a large interval of the second derivative over this thing. And in that manner, we get this thing will penalize it if it finds a solution where the sum of squares is a little bit higher, but this is compensated by the wiggliness being a little bit lower. The sum of these two might be smaller. Hence, if we minimize this joint objective function, we might get a better solution than if you minimize only this thing. And this parameter lambda, which we can freely choose, tells us how we want to relatively weight our two goals. One goal being that the least square should be minimal, so that the curve it gets close to the data, and the second meaning that the wiggliness should be minimal. And which of the two goals are more important is determined by this lambda. So in R, there is a function called smooth spline, which does exactly that. If I call this smooth spline, I give it the x and the y, and I tell it how many basis functions it should take. So each of these gray lines here is called a knot, and I told it to make a basis function with 20 knots. And if I do that, then if I do this, then this fit will produce me a fit which does this here jointly. You might wonder a bit, where does the lambda come from? I said it's a parameter that you have to specify. The smooth spline function allows you to specify it, but if you don't specify it, R has some clever heuristic to choose a good lambda automatically. And we take this heuristic for our first attempt, and only later we'll look how to make this better. So here's the lambda parameter, and it says here, if the lambda parameter isn't specified, it will make some clever heuristic to find a good lambda, which makes a nice smooth thing. And as you see, it has made a reasonably good result here. Yeah.
Can we still solve the loss explicitly, or is it kind of gradient descent?
That's the nice thing. We can still do it explicitly. It's not a gradient descent, and that's why these spline regressions are so popular, precisely because they are designed in a way that we can do the loss in one go, and I want to show you now how this works. So, and for this I have to tell you how this basis function is constructed. And these basis functions have a funny origin, namely from the automobile industry. Where do I have this? Where was this nice picture? Here. Before the advent of computers, when engineers made a plan for some machine or something, or like a car chassis, you remember in the 50s, there were all these bendy cars like the Volkswagen Beetle or this Citroën 2CV, the Ente in German, and so on. And that was the tool that draftsmen used back before the advent of computers in order to make such nice nice swinging lines. They used a piece of thin wood, which they put between two supports, and then they could just follow that. And of course, with the advent of more numerical techniques in the 60s, the question came up, how can you construct something with a computer, which is something like that? And the typical names that are associated with it are engineers or mathematical engineers. A guy called Bézier, who was working for Peugeot at that time, de Castelhau, who was working for Citroën, and Bézier, and the third one was de Beer, who was working for General Motors. And I will now show you what these three came up. I think they came up with it independently. They had more or less the same idea, and then they brought it together. And maybe so that you have a feeling of where this thing goes, I first show you a nice little animation, which I hope I find it again, because here, yes, that was the animation I did last time. So, imagine you have 2 points like this one here. You can draw a line through it, which is sort of a linear interpolation from here to here. So you can write the line equation of this thing by saying, I have a function t, which goes from 0 to 1, and this is sort of a mixture ratio that I have always 1 minus t of a first point and t of a second point. And if I let t run from here to here, I linearly interpolate from this thing to that thing, as they show here. So, and now let's make a second point, and let's assume that we have 2 points. They linearly interpolate from here to here and from here to here. By this we get these 2 points, L0 and L1. And now we also interpolate between these 2 points by saying the line from L0 to L1 should also be interpolated by saying, as you can see here, we always take 1 minus t from L0 and t times from L1. And in this case, the point in the middle moves from here to here, but it moves along a line. And obviously, because we have the green line interpolates between the gray lines and the red line interpolates between the green line, the x and y coordinates of the red line are quadratic polynomials in T. And this is what the Bézier curve is. Each of these two are quadratic polynomials. And if you want cubic polynomials, you just go one step further, you add another point. Now you have 3 beginning lines. You interpolate between these 3 gray lines to get 2 green lines. You interpolate between these 2 green lines to get, let's see, a blue line which now moves between all of them. And this is how we work with this. And you will see in a moment, you can keep this at the back of your mind. This is a 2D construction to get something which stretches through 2D space. The spline basis that I've shown you before is for 1D. So it's only because you can imagine you have now a cubic function for the x coordinate and a cubic function for the y coordinate. And what we are now having is a cubic function only for one of the 2 coordinates. And we put this together to a 2D or a 20D solution later. So this is called Bézier curves. As I said, was developed by at Peugeot to make nice car shapes in the 60s. And you might also know it a lot from graphics programs, all these vector design programs where you can do these kinds of things. And how do these now work? As I said, we start by always adding 1 degree up. So here, in my 1D case, this is now my 0th degree basis. It's just constant function. The first function is constant between the first to the second knot. The second function is 1 between the second and third knot. So each function is 1 between 2 adjacent knots and 0 everywhere else. And now I make a new function, the first degree basis, where I always make a linear interpolation between one of these constant bases and the next constant basis. So the first basis function will be a linear interpolation of this first and this second, gives us the first and the second level. And as you can imagine, if we interpolate between something which is 0 and something which is 1, we ramp up to 1 and then we ramp down again. Now we get these functions here which are all linear and they are all triangles. They go up and they go down. And now we repeat this process and say we add up, we interpolate between the black one and the red one, going up with one and down with the other. So we make a new function which lets t go from 0 to 1, and for t equals 0, we have 100% black and 0% red, and for t equals 1, it's 100% red and 0% black, and with that way, we let t then run from here to here to get a function which goes over this thing. And what you then get is this black function. So the black function is the linear interpolation between the black triangle and the red triangle, always progressively taking less from the black and more from the red one. And then you get this one. And of course, you do this for all of them. So they all have exactly the same shape, and they all have this thing. You can also imagine that these are quadratic polynomials, but they are piecewise quadratic. This here is quadratic, this is the second parabola piece, and this is the third parabola piece. But at every knot, we switch from one parabola to the next. Because this is easy to see why this is the case. A parabola should have constant curvature, and we can already see the curvature of this thing here. The first derivative should be linear, and the second derivative should be constant. And of course, the second derivative, which is this, switches every gray line. And you can also see it here. It has a constant left curvature, then it has a constant right curvature, and then again a constant left curvature. And now we repeat this process once more to get third-degree polynomials, which now have a support going over 4 of these segments between knots, up and down again. And the curvature will now no longer be constant, but will slowly ramp up and down again. And one more thing, as you can see, at least in the middle side, when we get away from the edge effects, here I've always added up all these lines, and the gray line is the sum of all the individual points. And as you can see, they all add up to 100% to 1.0, at least between this knot and that knot. We have to sort of jump over the first 3 outer knots, and inside these, it's all up to 1. And here we have to omit the 2 outer segments, and here we have to omit 1 outer segment in order to see the part of the basis which adds up to 1. And that now gives us a nice basis that we can conveniently use to build up our functions. The fact that it doesn't add up to 1 everywhere is a little bit annoying, and depending on your application, it might be that you are happier with this thing where all basis functions have the same shape, and hence you have the same kind of local properties everywhere along your curve. Or you might want where you push the outward knots in so that they sit all on top of each other. Like I say, these first 3 knots, I put them all to 0, and these I put them all to 1, and then I get my area of where the curves add up to 1 will stretch the whole support from 0 to 1. And that's what I've done here, where I say I add them up, and then they go in here. Now, how does this actually look like in code? Here is my first code, where I simply say the function b is naught is sort of the bottom line. I go from 1 to m. M are the 13 lines that I have here, and I say it's 1 whenever I'm to the right of knot I and to the left of knot I plus 1, and otherwise it's 0, and so I get these here. Then what I next do is to get my triangles, I add them up by letting t run from one to the next. So here you see xg, that's again my value which goes from 0 to 1. Here it's always how far to the left we are of the first knot, and how far it is till we reach the over next knot. And I divide this by the distance between 2 knots, so that this whole thing slowly ramps up from 0 to 1, and this thing ramps down from 1 to 0. And I always, while ramping up, I take the left spline, and while ramping down, I take the next spline. And S is always a new spline where I construct. And that way I get this triangle. And I use exactly the same formula as here in order to make my next thing, only this time I always have to jump not 2, but 3 knots ahead. So instead of S plus 2, I have S plus 3 here. and the last one I jump 4 spots ahead. This construction of always jumping a little bit ahead, you see it's a recursive construction. To get the 3rd-degree splines, I use the 2nd-degree splines, and to get the 2nd-degree spline, I use the 1st-degree spline. That was the bear who came up that you could make this in this way. So the Bohr formula. He just put all this together and said we can easily say the basis function of level, the ith basis function of level P can be written recursively constructed from the basis level functions of the level below by this thing. And I can simply write off this formula into my R code. And then I get here the de Boer formula, where I have my recursion end for the zeroth level, which just does the constant function, and the others are just these here. And if I add this up, I can use this function to again make this last plot. What I can also do, as you can see, it always takes this vector of the knots, and at the beginning I put the knots equidistant. That I said I have 10 knots, and there's always a spacing of 0.1 between the knots. But of course I can also make them non-equidistant. That's, for example, what I would do if I do this YouTube video that we've just seen, where we had this, where we said we had our knots for the x-axis here, 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 and here. So we would take the x-coordinates of these 4 points as our 4 knot positions for the x-spline, and then we take the y-coordinates for the y-splines. Doing that, and one thing I can do is, what I now do is that I say, I make my splines here from 0 to 1, and then the outer 3 ones, this, and this, I move all the way into 0. So that it's a little bit easier to say I put them a little bit to the left of 0, to point minus 1,000, minus 2,000, minus 3,000. And these here I put 1,000, 2,000, 3,000. So you see here, I spread out the outer levels to make them farther, and here there's 3 lines on top of each other. And when I do this, then I switch from this upper curve to the lower curve down there. And this is exactly how we get from this curve, which adds up to 1 only in the middle, to that curve, which adds up to 1 everywhere, by pushing together the parts where it doesn't add up to 1. And now we have this spline construction. And this gives us our basis function. And as you can see, we can use this simple formula, which is just the de Boer recursion formula, to calculate the value of a spline for all our data points, and use this to make the model matrix that we put into our linear model. But we still have the issue that we want to make sure that this curvature parameter is easy to calculate. And how does this now work? To find out what is the curvature of this spline basis, I can do 2 things. First, I can stare a long time at this thing and say, okay, I have to take the second derivative of that, and for this I have to use product rule with that x, and then bloop, and hopefully get it right in the end. The second possibility is that I scroll down a little bit, where it says the second derivative is, I think in the German version of this, I can scroll down a bit, and at the bottom I somehow find here the formula for the Cave derivative, but I can also simply do the fact that I use the fact that I've loaded it on my computer anyway. So instead of I simply draw my spline basis here again. And I simply calculate the derivative numerically, which is something which in math people usually don't like. They do everything with paper and pencil, but sometimes it really helps to just get your computer to calculate it, and then you can still afterwards try to prove that you got here, that this is nice. And this is a great example where this is the case, because here I have now here this spline basis, and I want to calculate the second derivative of this. And I have already calculated this thing at a grid of x values. So how do I get the first derivative? I always take the value for the function value at one x value, have a function value at the next x value, calculate this minus the value right above it, divided by the distance between the x values. And in order to do the same with second derivative, I now say the first derivative is y is function at x plus delta x minus function of x over delta x. This is obviously a finite difference, and I will let delta x go to 0 when I get my derivative, but let's not bother with the lemmas. Let's just say this is the first derivative, and I want to know how the first derivative changed, how I get the second derivative. So I just say the x minus delta x. This here is the first derivative, just one delta x to the left of here. So this should be a good finite difference approximation of a second derivative. And if you put this together, you will notice this is f of x plus delta x minus 2f of delta x plus f of x minus delta x. So, standard finite difference calculation of a second derivative. That's what you always do if you want to calculate a derivative numerically. So we simply do this. I do this here by telling it, take my matrix of values, take the values two rows up, one row up, and one row, and the row where I am, and subtract them according to this formula. One row up minus the row in the middle plus minus 2 times the row in the middle plus the row at the bottom. And then I get here a matrix of second derivative values. And I plot this. And what I then get is this here as second derivatives. And you see each of these things, they have of course all the same second derivative because they all have the same shape. And the shape of the second derivative is always going up like this. Going up from here to here, going all the way down here, all the way up again and again here. So this zip function. And all I now need to calculate is the slopes of these things. So actually only two slope values, this value and these values. And if you do this a bit, when you come, so here this is the second derivative. If we use the other version where we have moved in the 3 outer knots to the middle, then everything looks a bit more strange, but I mean, it's still the same. And you can easily imagine these slopes that should be possibly easy to calculate. We can now read them off from our thing and say it's numerically okay. But of course, it's obvious that it's just a matter of staring at your paper for quite a while, making about 1 million sign mistakes, hoping that they all compensate, and then you should get the correct values for these slopes. And with these, you can now easily calculate the curvature of the second derivative value at each position. And with this, we can now look back again at our function here. This was what we wanted to calculate, the integral of a second derivative. So here is the 2 second derivative signs missing. We calculate them by saying this is the function times is the second derivative times itself. So please imagine here a double apostrophe. Here it should say second derivative. I've forgotten the 2 primes. And I can say this prime function, the second derivative can just be constructed as a linear combination of these basis functions. And the linear combination of these basis functions, because I square them, I write them here twice. So this sum s runs over the basis function. bs3 are these basis functions. And beta s is our coefficient in front. And and this is the same thing again, and this we can now turn around and can say what we have here is a sum over, a double sum over all the basis function and again over all the basis functions. And here we have this integral, which is the integral of the product of one second derivative with another second derivative. So BS3 is now supposed to, I somehow have written this here stupidly wrong. BS3 is now supposed to be the second derivative of basis function S. So again, imagine here the two missing primes and here the two missing primes. And of course, this is something you can calculate ahead of time. For each pair of basis function, you calculate what is the integral of the product of its two second derivatives. And if you take the product of any two such basis functions here, you can imagine the product is a quadratic function from one knot to the next, and that is easy to integrate up. And so in the end, this whole thing here is simply a fixed constant matrix. Once you have fixed where you put your knots, this thing here is just a matrix of n by n values, m by m values for each pair of basis function, one value. And by which in this matrix you simply have to multiply with your coefficient vector, once from the left and once from the right, to get this curvature. And that's now the nice thing, that we can calculate the curvature of our linear combination of basis functions just by using this curvature penalty vector P. So if we go back to our total objective function, we said we want to minimize this term L here, which is the least square sum, and the curvature integral. The least square sum, we can say, we have to take here, we take here this matrix X, and the matrix X is the matrix formed by evaluating the m basis function on the n x values of the data. And with this, we get an m by n matrix of basis values at the data x values. And if we multiply this with the betas, we get the corresponding y hat values, which we want to compare with the original y values, which I put together into this vector. So y minus x beta, this is just this thing here. And of course, I square it, and I write my square by saying this is a scalar product of this vector with itself. And as I usually like to do it, I write my scalar product with saying a row vector times the same vector as column vector. And on the right-hand side, I have the same with this lambda and then the beta t beta. And as you can see, I can now rearrange this and say we have this yty, we have minus 2 times beta t x ty, and beta t times, and now I put here the product of these two x's and the product of this p together. And that's now the beautiful thing, because imagine we wouldn't have this term here. Imagine we wouldn't want to have a curvature penalty. Our lambda would be 0. Then this lambda p would vanish. So it's more or less a very similar equation as we use for ordinary least square. And so what do we do with it? We want to calculate, we want to find the minimum of this L. In order to find the minimum with respect to beta, we have to take the gradient of L with respect to the coefficient. So I do this, we take the gradient of L with respect to the coefficients beta, and that always takes a bit getting used to. This is of course constant with respect to beta. Here the beta t vanishes, so this is linear in beta, so we simply get minus 2xty, minus 2xty. In this quadratic thing, it's 2 times the linear term. So 2 times xtx plus lambda p beta. So this thing here and this thing we now want to set to 0 to find our minimum. And if I set this to 0, then of course I can put this on the other side and can say I want to solve this expression. Xtx plus lambda p beta is xty. And that is what we call the normal equations in the context of linear models or of ordinary least square. Because this thing here, xtx plus lambda p, once you have pre-calculated your p and you have calculated your x, and also decided on a penalty coefficient lambda, this is just a fixed constant matrix that you write here. In this xty, you can also calculate immediately. You take your data vector y and your xt, and you carry out this matrix vector multiplication so that you have the whole thing simply a matrix times an unknown vector is a known constant vector, ax equals b. This is a completely ordinary linear equation system that you can solve with Gaussian elimination, how you've learned it in high school. Or if you're a computer, you don't use Gaussian elimination, but you use QR decomposition, which however is exactly the same as Gaussian elimination. You remember in Gaussian elimination, you want to get in the end a triangular scheme so that you can back eliminate. And you have to keep track, and if you do it in a computer, you have to keep track of which row you have to which of the rows you have to multiply it with this factor and add it to which other row. And you can make all these operations, you can write them as another matrix, which just captures these operations of which matrix row you have added to which other matrix row. And this is the Q matrix. And when you have one Q matrix, which scares all this, and your triangular matrix, that's why you call this QR decomposition, or sometimes also LU decomposition, what the computer does when he tries to solve an equation system by Gaussian elimination. But it's essentially the same thing. And so we do this, we run this with QR decomposition, and then we get our beta. And if you use a normal linear system without any penalty, then your computer does exactly the same, only you omit this plus lambda p here. And the last question is now, how do we get a good lambda? And here, once we've written it in that way, we can see what scale we have to think at the lambda. If we want to make sure that both of these terms have about equal influence on our penalty, then the size of the magnitude of this matrix xtx and the magnitude of a p matrix should be the same. A good thing for the magnitude of a matrix is its trace, and hence you simply say, let's take the trace of xtx, the trace of p, and say lambda should somehow be a small multiple of the ratio of the traces of xtx and p. And that gives you a lambda, and I think R has some heuristic that it looks at how many data points you have and then say lambda is n squared times this thing or something like that. So, and that's sort of the beauty of linear regression, that even such a seemingly not at all linear problem like finding a smooth function which follows this very not at all linear data cloud, even this can be solved with linear regression by just solving a linear equation system. And this is the classical way how this smooth spline function works in R. And to finish it off, just for completeness, I want to show you one more alternative, a little variant to this smoothing spline. Or first, is other questions about this, what I've just shown? Yeah.
Is P a symmetric matrix?
Say again?
Is P a symmetric?
Yes, it is. For us, look at how we construct it. Here, you remember P, the elements of P are these integrals of the products of the second derivatives of two basis functions. And now, of course, if you swap them, it's still the same product. Yep, and that makes it, of course, easy because when the whole thing is symmetric, and we know that there should be a good solution. So, one issue with the spline regression is so this way of doing spline regression is probably the more popular one, but it has a bit the issue if your X is very inhomogeneous, you either have to move your knots around, such that between any two knots is about equally the same amount of data points. And nevertheless, sometimes you have this issue that you don't quite know how much of a spline basis you want to make, because if you make too many, if you make too big bases with too many basis functions, then it still tends to be a bit wiggly. And so people have suggested an alternative way, and there seems to be a bit of debate among the literature of practitioners of which of the two ways are better, so I show them both. the other idea is instead of penalizing the curvature, we penalize the change in coefficient from one beta to the next. You can imagine why this makes sense. If you have something like this, and it depends maybe a bit on what kind of data you have. If you have a data where you have the feeling this is data that doesn't make too much wiggles when you want to do on curvature. But what you also have is you have data where you don't want to fall for outliers. Where you say overall the data should not deviate too much from constantness. It should maybe go up a bit and go down a bit and up, but it should stay more or less at the same level. In that case, what you want is that you say, if I go from one spline to the next basis function, I don't want the coefficients between change too much, because whenever the coefficient changes a lot, the function will drop. But if you want to avoid the function dropping too steeply, so essentially you want to avoid too strong first-order derivatives, then an easy way would be to say we penalize the difference between adjacent coefficients. That's what we do here. So I say I want to penalize with beta s plus 1 minus beta s, so always the difference between the coefficients of two neighboring splines. And then I have this thing, and now the nice thing is again, I can again solve it with exactly this equation as before. I only have to think about how I translate this thing into a matrix P. And if you look at this matrix here, with twos in the middle, minus ones here, and one up here and here, this reconstructs exactly this sum here. Takes a bit of looking at it. I also spent some time looking at it. After a while, I realized, yes, this is really this thing here. And I tried this out. I made a basis function with really very many spline functions. I don't care if it's too many, because now I know if two basis functions, if I have too many, then the penalty will just keep them all at the same level. And when I constructed my P matrix with the twos in the diagonal, the ones here, and the minus ones outside, for these many things, I calculated the matrix, and this time I wrote the matrix explicitly, what we had up here with xtx plus lambda p. Let's see, that's what it says here. Where was I? xtx plus lambda mal my P matrix is on the left-hand side of my equation system, and the right-hand side is this vector, and I want to solve this. Note, in many textbooks, you often see something called the hat matrix that says you have to apply your data vector y from the right to this hat matrix, and then you get the beta vector. This is what you don't do. What you in reality do is you solve this equation system. And the solve function just uses Gaussian elimination to solve this equation system. And if I do this, I get this plot, and as you can see, it also works reasonably nicely. And what I can now do is sort of penalize the first thing. You see, I have increased and decreased lambda. This is if lambda too big, so that it doesn't allow the function to go up and down. This here is with lambda too small, that it wiggles too much. And somewhere here is a lambda in the middle, which works just fine. That's what I've done here. I've just called this lambda function for lots of different things. So now we know how to smooth in 1D, and we can go back to our 30-dimensional PCA space and see how we smooth there. And that's what we did last time. You remember we had here our single cell data set from this adult neurogenesis, where we said here are the neuronal stem cells which become activated when they enter the cell cycles and divide in order to produce many copies, and when they become neuroblasts. And finally, the neuroblasts turn into neurons. And we thought there should be something like a continuous trajectory of cells starting here and moving all the way to here. And what I now want to do is get a curve which goes through here. And our question was, how do we do this, that we get a curve through this 30-dimensional PCA space which follows that? Obviously, I shouldn't try to plot this curve in the 2-dimensional UMAP, because that's maybe already projected down too much. I should do this in my 30-dimensional PCA space. But in order to explain what's going on, it's easier to explain this in a 2D space. So let's make a little example case where I where I show you in 2D how to get such a curve through a data point. And to do this, I have made this data cloud here with gray points. And I want to find this dashed blue line which goes through the middle of these data points. And as you see, this dashed blue line, this is not a function of mapping x to y, because you see it curves backwards here. I did this in order to remind me that you should read this now as a vector-valued function which maps t. So t runs from 0 to 1 along this curve, and it's a curve, a vector-valued function which maps the unit interval to 2D vectors, and later it will map it to 30D vectors in our PCA space. And our data points are these individual 2D vectors which are marked by the gray circles, and I want to find a curve which goes through the middle. And in order to have example data, I did the thing backwards. I started with a curve, and I added noise to the curve. So here you see how I did this. I started off by defining knot points, and when I did what I told you before, I used B-splines to interpolate between these knots in the shape of a 3-dimensional Bézier curve, always interpolating along 3 consecutive ones, and with this I get this blue curve. I don't want to dwell too much about how I get the blue curve. It's just a sort of backwards way of using, again, our B-spline basis. But in the end, I get this blue curve, including its little back things, which helps us to remember that this is a curve and not a function of x to y. And I add to that now my noise, and just a random noise that I've put here with standard deviation 0.1, and I add this to both the x and the y coordinate, and then I get these gray values. And in R, there is a package called the principal curve package, which goes back to principal print curve. It seems I don't have it installed. Curve. Principal curve. I use this function here, which goes back to an idea. This time it's not automobile engineers of the 60s, but it's Hastie and Stützle of 1989. So for mathematics, this is nearly contemporary, something from the late 80s. And I want to show you the idea that they came up in this thing. So, and we first simply try out this curve. So we have this vector x, and x is simply, I should probably load this thing so I can show you this right at it as it's running here. Principal curves, here we go. My example data with the knots. I add a spline basis, and now here I add these x values, and you see x is now just a big matrix with 1,000 data points, and each data point has 2 components, an x and a y coordinate, and these are these gray values here. And I give this matrix to the principal curve function, and when it does something, it gives us here back something which it claims is a principal curve. And this principal curve here, you see it has a lot of strPRC. As you can see, we get a lot of stuff here. we get a list of points S. These are the projections of the individual data points to the curve, so to the nearest curve point. Ord is the order in which, so this first point is point number 712 in the list of all the points. Lambda is how far the projection of the point is along the curve, measured as curvilinear integral from the starting of the curve. And yes, the rest is just various other stuff. So here we get this curve that we get, and as you can see, the brown curve sort of follows the thing, but not very well. Now, what I can do, I can tell it that I want more degrees of freedom, because the thing does internally a spline regression, and you'll see in a moment how the spline regression works, and we have to tell it how big the spline data should do. And by default, it tries with 3 basis functions. That's way too little. So I tell it try 10 basis functions. And then the brown curve really nicely follows this dashed line. So how does this work? Here is the overall algorithm for the principal curve. We want to try a curve from the unit interval in our target space, R to the n, at the moment R to the 2, and afterwards R to the 30. And we start with some initial guess for this curve. And a standard heuristic is simply to do a PCA and take a line through the origin as the starting point. But you can't use anything else. It's as usual with all these iterative things, you have to get a good initialization to get the thing started, and then it runs nicely. And now you repeat until convergence the following iterative procedure. First, you extend the curve by linearly extrapolating it of both ends, making it a bit longer. So, where's my points? Points. So let's say I have this curve, and for reasons which will become apparent in a moment, I have to extend them and make them a bit longer on both sides by just extending the last bit. And then I have my data. Let's say the data looks like this. I project each point onto the curve. So for each point, I find the closest point on the curve. If the curve is smooth, then probably this should be perpendicular here, this distance vector and so on. So each point here, x, has now a projection point, and I identify the t value, because remember this is t is naught, and this here is t is 1, so this is how my curve works from here to here, and I find the curve point that is closest to there, and this curve point has, of course, a corresponding parameter value t, and that's what I now call the pseudo time of this point here. And, of course, the curve evaluated at this time, at this point, will be the projection point. So this is what I do. For each curve point, for each data point x, I find the closest curve point, and I store the parameter value that generates this closest curve point, and I call this the pseudo time of data point k. And this now, if I now order the data points by this pseudo time, I bring them in the right order, because this is a non-trivial part. When you look at this, you might think it's obvious. This point is to the left, this point is to the right. But when you have your data matrix, they are all in a random order. Maybe the first in the matrix row is here, the row 2 has this, row 3 has this data point. So you have to bring them in the right order. And this now gives you an ordering of the points, at least a preliminary ordering, because now we have to iterate this. What we now do is that we fit a new curve by regressing each coordinate of the xk onto their corresponding t values. So I make now a new scatter plot, where this here is the pseudo time values, so the curve parameters for each data point, and this is one coordinate of the data points, maybe the x coordinate. And then I get this thing here, and this will become the x component of my curve. And then I do the same for the y coordinates of all the points. So this turns to another component and this stays. And then I get a new curve. And from this I assemble my new function. And this is what this thing here does. And now let's try to do this ourselves. So we first need to initialize. And to initialize, I said, let's make a principal component analysis of our data. So I have here my principal component analysis. And as you can see, it gives me here the direction of a first principal component. And you can just read this as a slope of a line because I'm in 2D. Otherwise, it would be the vector of this. So here I've drawn this line here with a slope given by this x and y coordinates. And as you see, it slopes a bit down. And I have adjusted the intercept of this curve manually that it goes roughly through the middle. But actually, it doesn't matter where I put it because in the end, when I project the points on the curve, and no, actually, it does matter. So I have to put it such that it goes reasonably well through the middle. And I can take, of course, now PCA $x gives us the scores of each data point in the corresponding principal components. And this is a decent first check for our pseudotime vectors. So I say these things here, which is essentially the projection of each data point on this line here. If a line goes through the middle, this thing gives me a first ordering of the points. And you can see the ordering will be a little bit wrong. For example, this point will come later than this point. So here the points get backwards. I can show you here how the ordering looks like by making this nice. I found some nice colors to show you this. Here, these colors, they go from dark to light and always go twice through the rainbow. And you can now easily see all these points are have the same pseudotime because they have the same color. And now let's do the regression. So for the regression, I use again this smooth line function here, the one which we've just learned how it works, and fit each of the two components, the x and the y components of our data points, to the pseudotime. And now, if I do this and plot this, then you see here, these red lines, they now connect they are now formed by the two x and y coordinates. So that's what I've done here. I have done this fits here and fits X1. This is for the x-axis and this is for the y-coordinate. And for the x-coordinate, I can now look at, oh, have I actually done this? Fits X, yeah. Here, this is what I've done first here. So here you can see the smooth curve fit. So this is the x-coordinate plotted against the pseudotime. And this is the y-coordinate plotted against the pseudotime. And you see the x-coordinate, we have here this doubling back, which doesn't quite work. And for the y-coordinate, it works a bit better. And if I now do this, I can now construct my pseudotime thing by saying, I ask, what are the projections from here to here? So I have these PT values that I got out of a PCA scores. And range PT, you see these are values from minus 2.4 till 2.7. I take this thing and add about 30% to the left and to the right of this range and make me a new range of values, TG, which now takes here this range from minus 3.9 till 4.3 and makes 10,000 places. And I evaluate my two splines, this spline here and that spline, so these two red lines, I evaluate them in all these values. And I get here these 10,000 coordinates. And these 10,000 coordinates I can now plot. And why doesn't this ever work? Now we see our actual spline fit. It's a bit stupid because this is the actual spline fit. This here was only the y-axis. it's not the same. It only looks, it looks similar, but it's not the same. So this is now our actual first curve here, which we have. And as you can see, because I have extended it a bit to the left and to the right, it goes further out than the data. And because we use spline regression, it makes this nice effect that the splines, if you evaluate them outside their, sorry, it's not spline regression. Do I use spline regression here? Or? Yes, I use spline regression. The splines, if I go a little bit outside their boundary areas, they just continue linearly, and that's why we get this here. So, and now comes the projection step. For each point, I have to find where does this thing project on the curve. And when I wanted to do this, I first thought, oh no, now I have to calculate an orthogonal projection and do something clever. But then I thought, let's do it the primitive way. I've just calculated the value of 10,000 values on this red line. And you remember from 2 weeks ago, we had this nearest neighbor package. And the nearest neighbor package, it allows you, it also has a query setting where you give it 2 lists of points. The first of list of points is our data points, and the second is the query points. And then for each query point, it finds the 10 nearest neighbors among the data points. And I call this thing here by telling it, use the curve points, the 10,000 curve points as data points, and my 300 data points as query. And for each of these 1,000 data points, find the closest points, I only want one nearest neighbor, find the closest point among the 10,000 curve points. And that's what I now have here. This index here, which tells us that the first data point falls at position position 0.42 because it was of the 10,000, it's the 4,200th. And I also get the distance. This is the projection distance from the point to the curve. But what I typically want, the pseudo time, should not be simply should of course be the distance from the starting point measured along the curve. So what I now do, the curve is made up out of all these equilinear things. And if I now have projected, say, onto this point, then I wonder how far is this point from that point. To this end, I calculate the length of all these individual line segments of these. You remember we made it from 10,000 points, so of these 9,999 line segments. To do this, what I do, I take this here, these are the 9,999 curve points, except for the first one, and these are all curve points except for the last point. So when I subtract then, I subtract each curve point from its neighboring curve point. And then I square these distances, sum them up, and what I now get here, after I take my square root, is the length of these 9,999 curve segments. And now, and here you see how long are these curve segments. They are all more or less the same, at least at the beginning. Oop. Are they actually always the same? Hist, curve segment, lengths. So, here. You see, this is why we needed to sum them up. They are sort of always about the same length because we did them with equidistant t values, but of course, the speed with which we run through the curve when we go linearly through t might differ a bit, and that's why we do this. And now in R, there is this CumSum function. What the CumSum function does is it takes a vector and it gives you back a new vector, which is first element, sum of the first 2 elements, sum of the first 3 elements, sum of the first 4 elements. So the list of cumulative sums. And this is what I get here. This is the first segment, sum of the first 2 segments, sum of the first 3 segments, sum of the first 4 segments. And I manually put a 0 in front, so that now I get here for each curve point, the distance of this curve points to the start. And that's why I had to put the 0 at the beginning, because the very first curve point, of course, is the start. And now, you remember, this here tells us it was the nearest neighbor search, which tells me for every data point, which curve point is the closest. And now I can ask how far is this curve point from the start. And now I get with this with pseudo-time values, which now tell us for each data point, how far is this data point projection onto the curve from the start. And now I have new pseudo-time values. And now I can go back to the other iteration step again. I can, first let's plot this. I now plot each curve, each point, according to its pseudo-time value. And if you compare this plot to the plot further up, you see with our initial thing, this still looked quite bad. Sort of these here, they all had the same pseudo-time value. And now after we finished the first iteration, with new pseudo-time values that we've just gotten, they now really increase along the curve. And we see that these have a different pseudo-time from that and that. And now we can start our next iteration. We can again now take, now regress each point onto this red line, but this time, now we do again do the spline regression. So for each data point, we take its x value and regress it on the pseudo-time, so onto the color. So in this plot here, this here, the x-axis is what was the color in the previous plot, and the y-axis is what was the x-axis in the previous plot. And the red line is the new smooth curve that we now got by calling the smoothing curve function the second time. And the same we do here for the y-coordinate, and there it looks like this. And then I put the x-coordinate and the y-coordinate together to get a new curve. And as you can see, the new curve now follows this backtick much better. So here I put now this whole thing together into one big plot where I say, to make one iteration of the principal curve algorithm, take here, you get here the results from the previous iteration, or if we're just starting, 0. If we are just starting and no previous data is available, run a principal component, extract the first component of the PCA and use that as pseudo-time, as initial pseudo-times. Then run for each coordinate, so for each of the dimension of our target space, run the spline smoothing algorithm. Then calculate a small grid of values around this to go over the range of pseudo-time values, and produce a new curve by evaluating the return splines for the individual coordinates along this grid. Then we have now curve points, 10,000 of them. And, or here, 10 times as many as we have data points, I've said. Then find for each data point the closest curve point. Then calculate for each curve point, calculate how far it is from the beginning of a curve by adding up all the segment lengths. Yeah, and with that, find out what the new pseudo-time is, and then report this, the new curve and the new pseudo-time. And if we do this, I can now call this thing a couple of times. And as you can now see, this is the first iteration. Second iteration already is quite nice. Third iteration now fills in properly. Fourth iteration, nothing happens anymore. So we have convergence after the fourth iteration. So if we want to improve this a little bit more, one thing we could do is that we think about, is it really necessary to evaluate this curve at 10,000 points and do this nearest neighbor search, or can we do something more clever by making less points, because to approximate this curve by linear segments, 1,000 segments should be plenty, but then maybe it could be that the best projected point is in the middle between two curve points. So what we would have to do is, if this is my curve, and this here would be a data point, and I project the data point here, before I would simply have said this data point is closer than that, so I use this one. But if I want to do it really nice, I could say, these are the two closest data points. Try to find the place within the two, which is the closest, which should be easy to figure out with a bit of geometry. I'm actually not sure what the principal curve function of Hasty does, whether it goes through this or whether it also does the primitive way I've now programmed, but that's something you can play a bit. And of course, the other way how we can improve this thing, this idea that we regress the individual coordinates, that we make a spline regression of the individual coordinates on the preliminary pseudotimes. This step, we can use any smoothing function. We can replace the spline smoothing with, for example, the local regression smoothing that we talked about last week. And in that way, the thing is quite modular. We can replace this part of the algorithm. And in fact, the print curve function allows you to just apply a smoothing function, and then it uses that, and you can compare which of the two results work better. So now we have everything that we need for our pseudotime. We first know how to make a 1D smoothing where we have y values dependent on x values, and we make a smoothed curve, and we know how to use this to make a curve through a high dimensional space. And that's what we've done now here in this trajectory thing, where we started off where we now want to make a trajectory through this thing. And I already showed you, I think a week ago, how I did this roughly. I said first, in order to not confuse our smoothing, I remove all these other cells which are not part of the lineage. So I kick out 4 clusters, 4, 8, 16, 15, 17, and 12. Also, in order to not get confused here by this double thing, I kick out cluster 6 and 14. So I'm only left with these here, and I actually deliberately leave in cluster 7 because I believe that they are really connected, and it's just an artifact of a human projection. And so these are the clusters I've decided to leave in. And what I now do is, here I kicked out cluster 6 and 11. And I run, okay, this now needs probably a while to load all this data, so I show it to you on my finished thing here. Where am I? Expression along pseudotime. So I call the principal curve package, and I give it here my data points. In my example before, I gave it a vector, a matrix with 2 columns for x and y coordinate. Now I give it a matrix with 20 columns for all the principal component coordinates, using only those data points which are within the lineage, so kicking out the other clusters. Yep. And here I told it that it should approximate the curve only at 1,000 points, because it tried before to approximate at as many more, and it took hours. And with this, it only took 10 seconds to make these things. Here, it always gives us the sum of the square distances, and we can see that here it has decided that it has converged. And now I plot this by plotting again my UMAP and coloring each cell by the pseudotime that the principal curve algorithm has assigned to it. And you see it goes round, round, round here, and when it jumps here to this little light green, and when it comes dark blue, and here something surprising happens. This yellow one, it actually thinks this is the beginning and not at the end. And now, what I now want to do is I also want to know what would be the pseudotimes of all these cells here, which I have kicked out. And to do this, I simply use the same trick as before. I take the curve points, so with 1,000 points that it has produced me here along this line, and the PCA coordinates of all the other points, and ask how far are we here, and then I can again implement this as a pseudotime. So I take here the so here, what it actually does here, because the principal curve algorithm, what it gives me back is the projection for each data point. It doesn't give me back what I had before, the equidistantly spaced values on the curve. But there's so many cells here that this probably doesn't make a difference. So I ask which of the of a colored, for each gray cell, which colored cell is closest to it. And then I assign the gray cell the same pseudotime as the colored cell. That's what I do here. And here I just rescale the pseudotime so that it goes from 0 to 1 because I find this nicer. And assign this now to the server's pseudotime variable. And then I can now replot this again. And now you can see these things here have gotten the same pseudotime as we have here in between. This thing here has gotten the same pseudotime this here, but these are the oligodendrocyte precursor cells. They have not too much to do with the neuronal linkage. Therefore, it might make sense because they also come out of the stem cells and will then proceed to become the oligodendrocytes here. But the question is this really appropriate to use these points and say we have this pseudotime? And the question we should ask here is, how far was actually the projection distance? Was it that these points are simply also close to the curve, or did we project from somewhere far away here up to here? So what is this projection distance? And that's useful to calculate. And because we have returned by the principal curve package, we have the individual original data points and we have a projection onto the curve so we can calculate the distance. So here, distance to curve, actually we don't have to calculate them. We got them returned when we made the search for the closest point. It also tells us the distance, how far the closest point is. So I get these here and I say this is the distance to the curve. And you see here the distance of the curve goes from nowhere, it's really 0. We have no point that really lies on the curve, but some of them are only 1 unit ahead and some are 100 units ahead. So I made this here a logarithmic distance scale. And then you can see the curve really runs around the yellow stuff. In the previous thing, I actually plotted the curve into it, but here I can't do that. Because remember, the curve lives in the PCA space. We've now fitted a 20-dimensional curve. And I have to bring this 20-dimensional curve onto the UMAP, but the UMAP is a nonlinear projection, and it's not even clear whether the UMAP is a continuous projection. So we don't know whether this would give a continuous curve here. So I opt for the next best thing and just color the points by the distance to the curve so that I can say the curve runs where the yellow color is. And what I can now do, that each point, each cell now has a pseudotime, I can do the following. I can multiply this with the row variance, calculate the row variance, and find the 10 genes with the highest variance of expression simply taken over all the cells. And these 10 genes, for each of these 10 genes, now I call this log-fit function that I've just done here. And then I get now here these curve values for each of my data grid of 1000 pseudotime values from 0 to 1. I get these values. And to visualize them, I don't use a 2D plot, but I use a heat map like this. Each line is a gene, and the y-axis of a fitted curve I code by colors. If you do such heat maps, it's usually quite helpful to standardize them in the sense that we say each that we take each row of values and divide it by the maximum, because then you can see more. Here each value is divided by the maximum so that they all go to 1. And of course I have labeled here my axis so I can see which gene it is. Then I thought another thing to make this look nicer is you find out where the maximum are and sort by them. So here I've now taken these curves, these points, and sorted them by the position of it. So I just reordered the rows, and because I was at it, I not only reordered the rows, I also changed the color scale to don't know which of the two is nicer. And then I decided to do it not with 10 genes, but with the top 100 genes, and got this plot here. And that plot now is something which really helps you now to do biology, because you can see here how which genes peak at the very beginning, like are typically of the dormant astrocytes, which genes mark the transition to activated astrocytes, when we see here this sudden jump to now the transient amplifying progenitors, which run through the cell cycle. And here the neuroblast genes, which now began to differentiate to find neurons. And we can here see which genes are active in each of these steps. And trying to understand what's going on there, that's of course now how we get data out of that. What we can ask here is, we have now simplified this complicated trajectory into a one-dimensional object by plotting everything against 1D. So the next question we should now ask is, what do we lose by essentially averaging over everything which is here orthogonal to this pseudotime curve? But we have reached the end of what I have prepared for today, and we also have reached the end of our 90 minutes. So let's stop here and see. Yep. Any questions about this, comments, remarks? Otherwise, an obvious question is this Wednesday, who will be here on Wednesday? Just so. What? Nobody has time on Wednesday? Because if nobody has time on Wednesday, we should move or skip them. Doesn't make much sense to do it for only 2 people. So it's really only 2 people who have time on the Wednesday. All the others, what do you guys have? Because at the beginning there were a few more, but you all have other lectures, right? And it's also, I was wondering on Wednesday whether we do exercise or